Okay, good evening, dear students. In last class, we discussed the limitations of first law, thermodynamics. Okay, in today's class, I am going to discuss about the different statements of second law of thermodynamics. A different way or variety of the great variety of way to state the second law of thermodynamics. Here in this defined stated the first law of thermodynamics and limitations of first law of thermodynamics, and next the second law of thermodynamics. The unit name is thermodynamics 2. The second law of thermodynamics. The second law of thermodynamics may be stated in a great variety of in a great variety of ways. Great variety of ways. Here, the second law of thermodynamics may be stated in a great variety of ways. Here, there are five varieties. Five variety ways are stated. The second law of thermodynamics. First one is a Kelvin Planck's statement. First one is Kelvin Planck's statement. Second one is a Clausius statement. Second one is a Clausius statement. And third one is Thomson statement. Third one is Thomson statement. And fourth one is general. Here we are considering the metallic bar statement. And lastly, the second law of thermodynamics. There are five variety of statements are there in the second law. Here I am discussing first one. Here the Kelvin Planck's statement. According to Kelvin Planck's statement, here they studied the cyclic operation of a heat engine. He studied the cyclic operation of a heat engine. We can know the second law of thermodynamics. Take the heat for a cyclic heat engine, and take a cyclic heat engine, then you able to state the second law of thermodynamics. It can easily understood from the efficiency of a corner. here it is easily understood for efficiency of Carnot cycle. Efficiency of Carnot cycle. Efficiency of Carnot cycle. Here he observed that the work done by a heat engine. Here the work done by a heat engine operating in a cycle is zero. After easily understanding for efficiency of Carnot cycle, he used the efficiency of Carnot cycle. He observed that the work done by a heat engine operating is the work done by a heat engine is in cycle for cycling process it is a zero is observed when the two temperature are same. When two used two temperature in two temperature the cycling process in a heat engine is the heat cycle process is formed it observed that is only zero and afterwards he stated the second law of thermodynamics. The second law of thermodynamics is stated as according to Kelvin Planck's statement. Here it is impossible for a system operating in a cycle and connected to a single heat reservoir to produce a positive amount of work in the surroundings. This is a second law of thermodynamics statement according to the Kelvin Planck's statement. And right here, it is impossible for a system statement. It is impossible for a system operating in a cycle and connected to a single heat reservoir heat reservoir single heat reservoir to produce positive amount of work in the surroundings. This is a statement according to. This is one mark important when in examination the question arises. We state second law of thermodynamics according to Kelvin Planck's statement. This is a one mark question. According to Kelvin Planck's statement, it is impossible for a system operating in a cycle and be connected to a single heat reservoir to produce a positive amount of work in the surroundings. This is a statement of according to Kelvin and Planck's statement. Next, second is a Clausius statement. Second one is Clausius statement. Clausius statement. according to Clausius statement. Here, according to second law, a heat engine operating in a cycles. Here, the heat engine is operating in a cycles can perform works only by observing heat from a reservoir. You are observing only the heat for a reservoir and at a higher temperature, and by rejecting the difference between the heat absorbed and the work done by the heat engine. Here you are rejecting the heat is absorbed, and by rejecting difference between the heat absorbed and the work done by the heat engine to another thermal reservoir and at a lower temperature. Thus here the second law is given by Clausius can be stated here. The Clausius statement, he used the operating cycle here, the engine operating, heat engine operating cycles, and he performed the works only by the absorbing the heat from a reservoir at a higher temperature, and also it is rejection takes place here. The rejection is the difference between the heat absorbed and the work done by the heat engine, and here to another thermal reservoir at a lower temperature, and here according to this process he is given the statement of second law of thermodynamics. The statement of second law of thermodynamics according to Clausius' statement, it is impossible for a cyclic process. Here also it is impossible for cyclic process to convert heat into the work without the simultaneous transfer of heat from a body and at a higher temperature to one at a lower temperature, or vice versa here. That is, it is impossible for a cyclic process to transfer heat from a body at a lower temperature to body at a higher temperature without the simultaneous conversion of work into heat. This is a statement according to Clausius statement, second law of thermodynamics. On other statement, I write here, it can be stated that it is impossible for an engine operating in a cycle to have as its only effect the transfer of a quantity of heat from a body at a lower temperature to body at a higher temperature. This is a statement according to Clausius. Yeah, I write this one, the statement of according to Clausius statement. It is impossible for an engine. It is impossible for an engine operating for an engine operating in a cycle to have as its only effective transfer only affect the transfer of a quantity of heat. Only affect the transfer of a quantity of heat quantity of heat from a body at a lower temperature at a lower temperature to lower temperature to a body at higher temperature at higher temperature at higher temperature. Here it is impossible, and here it is the effect of transfer is impossible. Here we are finding the difference between the work done and heat is transfer. So here the observed heat is impossible. Here the impossible for engine operating in a cycle to have as its only affect the transfer of quantity of a heat. Only affect on the transfer of a quantity of a heat a body at a lower temperature to a body at a higher temperature. This is a statement according to the Clausius statement. Next, third one, Thomson statement. Thomson statement. Okay, here according to Thomson statement, the second law of thermodynamics, you know that all spontaneous process, that is the spontaneous process is produced only in one direction. Spontaneous process means here is produced in only one direction. It cannot be reversed without the interconversion by an outside agency. This is one sided process for the statement for a second law of thermodynamics according to Thomson statement. Here it is a continuous until a state of equilibrium is established, and here according to this process the second law also be stated as the all natural or spontaneous process tend to go to a state of equilibrium. This is the second law of thermodynamics according to Thomson statement. Here, according to Thomson statement, here all of you know the what is meant by the spontaneous process. This spontaneous process is only proceed only in one direction. It is a one direction. It cannot be reversed. Here, one direction it cannot be reversed without the interconversion by outside agency. This outside agency, this is one-sided process. It is continuous until the state of equilibrium. It is continuation takes place here. It comes until the state of equilibrium is established. According to this, the Thomson statement, according to Thomson statement, the second law of thermodynamics is stated as the all natural or spontaneous process, and right here statement all natural process or spontaneous process, natural or spontaneous process, natural or spontaneous process tend to go to a state of equilibrium. Tend to go to a equilibrium. To go to a state of equilibrium. State of equilibrium. This is the third statement here. According to the Thomson statement, here all natural or spontaneous process tend to go to a state of equilibrium until the finally you get equilibrium is established. Here, according to this, the Thomson is stated as the second law of thermodynamics. Next fourth statement in general here. The fourth statement, if we consider fourth statement, if we consider a metallic bar here, the metallic bar, this is a metallic bar here. I imagine the consider a metallic bar and which is hot at one end and cold. There are two ends here. The metallic bar is a two ends. One end is a hot and another end is a cold. And here which is a result of flow of heat as acquired a uniform the temperature the original condition can be restored if heat is allowed to pass from one end of the bar. Here when heat is flowing takes place and heat is allowed to pass from one end. Here one end is a cold and one end is a hot. And here you take hot and here you take cold and here you are transferring to pass the heat from the cold condition here and end of the bar to a machine are capable of converting heat into the work. You are converting heat is utilized into the work here. This is the fourth statement. Here this is the work is converted by a friction into an equivalent amount here. You are using here the work is only here. The converting heat into a work. That is the work is converted by a friction into an equivalent amount and equivalent amount of heat which is then transferred to the other end of the bar. You are considering it is a metallic bar. There are two ends. Here this is a metallic bar and here one end and here one end and this end is a hot and this end is a cold. Here the hot is transferring here to the work here and some extra work is needed from an outside sources. Then to complete the reversal, this is need to be another form of stating the second law. Here this is the fourth statement for the second law of thermodynamics. The fourth statement is the heat cannot itself flow from a colder to a heater body. Here the heat cannot itself flow from a colder to a heater body without the interconversion of an outside agency. This is a fourth statement. Here I write the heat cannot itself flow cannot of itself flow it cannot itself flow from a colder to from colder to a hotter body. Colder to a hotter body without the interconversion of an outside agent. Without the interconversion often, interconversion often outside agency. This is the fourth statement of second law of thermodynamics. It cannot move itself flow from a colder to hotter body without the interconversion of the outer of an outside agency. This is the fourth statement. Next, fifth one. This is the last statement here. Fifth one, here the second law of thermodynamics can also be stated as the energy of universe remains constant. Here the energy of universe remains constant, but available energy is decreasing and entropy of universe is increasing to a condition of maximum entropy of randomness. This is a statement of second law thermodynamics, and there is a maximum choice of the under the previous itself. This is a fifth statement. Or prevail itself here. This is known as a second law of thermodynamics. Here the second law is it is the energy of universe remains constant. Here the energy remains constant. It is universe and the universe remains constant, but the available energy is decreasing and entropy of universe is increasing to a condition of maximum entropy of randomness. When there is a maximum, choose the under will be prevail itself. This is known as the second statement of second law of thermodynamics statement. This is the final statement, fifth statement of second law of thermodynamics. Okay, next, the spontaneous process. Spontaneous process with examples. With examples. New syllabus, spontaneous process with examples. And here the spontaneous process with it. You know the what is meant by spontaneous process. Here the spontaneous process which is actually occur in a nature or known as a natural or spontaneous process as they always tend towards equilibrium. Here, the spontaneous always occur here in nature and it is known as a natural, or here the spontaneous process as they always tend towards equilibrium. Here, always this process always tend towards equilibrium. This process tend towards equilibrium. In such a process, the change takes place in a system without aid of any external energy. It is a changes takes place in a system without the any aid of external energy. This process is changes here. And for example for this the example for this spontaneous process is the gas spontaneously moves from a higher to lower pressure. Here, example, gas spontaneously moves, gas spontaneously moves gas spontaneously moves from from higher to lower pressure, higher to lower pressure. This is an example for spontaneous process. Here, the spontaneous process is occurring in a natural. That's why it's called a natural process. And here, the natural process, the spontaneous process, natural process, or also called as a natural process. Always occurring natural process. That's why it's called as a natural process. Or a spontaneous process, and they always tend to a equilibrium, at equilibrium. And here, in such the process, these changes take. This process is changes takes place in a system without the aid of external, without the aid of any external energy, or without external agency. And for example, for this spontaneous process, is gas is spontaneously moves from higher to the lower pressure. The first is high, the so gas is contains it is a higher pressure, and here the spontaneous moving takes place here, the higher pressure to the lower pressure. This is very important for 1 mark question or 2 mark question. Here we define the spontaneous process and give an example here. Here, this is an example, and next another the solute diffuser. The solute differs from a solution of higher concentration to a lower concentration. Higher concentration of a lower concentration. A solute dissolves from a solution here of a higher concentration to the lower concentration is another example here. And another, these all are incidences of spontaneous processes. And another example I will tell here, the heat flows from a heater body. The heat flows from a heater body to a colder body. Here the heat is flowing from a heater body to colder body, and this is another example. And liquid flows from a higher to a lower level. Here the liquid is flows from higher to lower process to lower level here. And the all these spontaneous reaction, these all are the spontaneous reaction. This gas spontaneous moves from higher to lower pressure is a spontaneous process or spontaneous reaction. And solid diffuses from a solution of higher concentration to the lower concentration. This is also for example for spontaneous reaction. And heat flow from the heater body to the colder body. This is also example for this spontaneous process. And another, liquid flow from higher to lower level. This is also example. And these all are the incidents of spontaneous process. It happens according to the, or it happens due to the spontaneous process. And all these spontaneous processes reactions takes place in a direction and are irreversible, and everyday system moves towards the state of equilibrium. You know, you everyday like here the everyday system towards the equilibrium, and you will therefore the state that all spontaneous processes are reversible. Here, the all spontaneous processes are reversible, or all spontaneous processes tend to a state of equilibrium. Here, all the spontaneous processes tend to a equilibrium. The state of tend to the state of equilibrium. State of equilibrium, and the spontaneous process takes place, that is naturally without continuous outside interconversion. This is a spontaneous process, and here the spontaneous process may be fast or slow. Here, the spontaneous process sometimes it is fast and it is sometimes it is slow. Here, it is kept in your mind. Here, the spontaneous process is maybe fast or slow. And here, an expression is fast and spontaneous, and explosion it is fast and spontaneous, and the process of resulting is slow and spontaneous. Here this process is the process of this resulting process is slow and spontaneous, and example for this slow and spontaneous process, a drop of food coloring. We take the drop of food coloring. You know, the drop of food coloring will spread in a glass of water. Here, slowly. Here, this is a glass container. Here you have a water, and you add a drop, one drop of food color, and slowly it is spontaneously takes place. The resulting spontaneous process here, it takes place, the colorful color is, it gets a slow process and get a spontaneous result here in a glass of water. This is one example for slow and spontaneous process. And another example, ice melts in our heating. Ice melts, ice melts when heated. When heating takes place, the ice is melts slowly here. And another, the methane burns into oxygen gas. Methane burns into oxygen gas. This is an example. And another, that is ammonium chloride dissolved in the ammonium chloride dissolved in a test tube. You take one test tube. Here you take the test tube. Here in test tube, here you take in this test tube ammonium chloride, NH4Cl. This is the ammonium chloride dissolved in a test tube. You take an ammonium chloride in this test tube and dissolve in this test tube with water, making the test tube holder. With water, you add water and is connected with the test tube holder. You connected with the test tube holder and dissolve this ammonium chloride. This is an example. This is also dissolving in slow process, slow, and it may be slow or it may be fast reaction. The non-spontaneous here, the non-spontaneous process, it occurs by a supplying external energy. Here, spontaneous means it exchange or changes without external aid of spontaneous without external agency. Here it changes only without external agency. The non-spontaneous means the non-spontaneous process is it is applying or supplying the external energy to the system here. Non-spontaneous Non-spontaneous means here the non-spontaneous process occur by supplying the external energy to the system. This is called as a non-spontaneous process. And example for this non-spontaneous process is water is pumped from a lower level to a higher external energy. What example? Water pumped here. The water is pumped from a lower level to the higher level. This is an example for the non-spontaneous process. Higher level, you are using the external energies required here. Required external energy. Required external energy. External energy is required for the non-spontaneous process. This is a non-spontaneous process. Okay, I'll stop here only and continue in next class. That is remaining portion remaining are the Carnot cycle. I'll take this Carnot cycle in next class. Thank you.